there's an awful lot that one can do in Statgraphics with respect to setting up experiments, analyzing the data, and so forth. And it's a real good use of statistical methods in terms of being able to extract information in a efficient, cost-effective manner. Ever since I took my first course in statistics from Stu Hunter, which is getting on now to maybe almost 40 years ago, it really has been a subject that I've enjoyed talking about, enjoyed putting features into Statgraphics to help others do it. And as I went through developing the webinar we're going to do today, I noticed that there's actually more than 1 hour's worth of material to talk about. So what we're going to do today is go through a typical example of how you construct and analyze an experiment in Statgraphics. And I'm going to try to schedule another webinar in a couple weeks to cover some other advanced topics, such as robust parameter designs and interesting other special types of experiments that I just couldn't fit into the hour's discussion here. But this is going to be a quite interesting webinar. We have a lot of people signed up and a lot of people still coming on board here, I see. So I hope it's going to be useful to you. And I will try to keep it down to about an hour. We are monitoring the chat in the GoToWebinar so that if you have questions at any time, if you go to the chat section of that GoToWebinar dialog box, you can put in your question, send it off, and we'll be monitoring it during the presentation, responding to as many as we can while I'm talking. But if there are some technical questions that really need me to answer, we'll try to reserve a little bit of time at the end of the seminar to do that. Okay, so let's go ahead then and if we can start the seminar. I'm going to go through a couple PowerPoint slides here just to give you an overview of what I'm going to be talking about. That'll take me only, I hope, about 5 minutes, and then I'll quickly jump into Statgraphics so that we can actually go through live the process of setting up and analyzing an experiment. The way Statgraphics is structured, if you're using the newest version of Statgraphics, we have added to the program something called the Design of Experiments Wizard. Previous versions of Statgraphics through version 15 contain the facility to set up and analyze various types of experiments. They also set up the ability to optimize multiple response variables and so forth. But before version 16, you needed to go to several different menu items in the proper sequence to go through the entire process. What we did in version 16 was to develop a wizard with a special toolbar which tried to bring together all of the pieces of the experimental design process so that you could stay in one place and just sequentially go through the basic process of DOE. Now, the way the Design of Experiments Wizard is constructed, you'll notice that there will be 3 phases, and I'll be talking about experimental design through these 3 phases. The first phase is when one creates the experimental design. Before you've gone out and collected any data, done any experimentation, you sit down and you decide how many runs you're going to need to do, what the settings of the experimental factors are going to need to be, with the goal of trying to get the most information out of the fewest number of experiments. Obviously, in the real world, experimentation is expensive, it's time-consuming, and so forth. And we find out very quickly that not all data is created equal. You can collect, if you collect the right data, then often you can get more information out of a smaller number of observations. provided you collect the right data. And that's really what experimental design is all about. Setting up your data collection effort, your experimentation, so that you can get the most information out of the fewest number of experimental runs. And phase one is exactly that, sitting down and planning the experiment, what data I'm going to need to collect. Phase two occurs after you've done the experimentation. Once you've actually gone out, collected that data, you need to come back to your statistical program, come back to Statgraphics, put in the results, and then fit various types of statistical models. As part of the analysis, you may want to try to optimize the process as well. And then phase three has to do with further experimentation. If you're not completely satisfied that you understand everything after phase two, there are ways to augment the experiments that you have done to do additional experimentation. Okay. Now, as far as phase one, in version 16 of Statgraphics, we've defined 7 steps to creating an experiment. And as you'll see, the Design of Experiment Wizard will quickly take you through these 7 steps. They basically have you define the response variables you're going to measure, the experimental factors you're going to be changing. You'll select a design. You'll specify the statistical model to be fit. In cases of a de-optimal design, you'll select a subset, perhaps, of the runs that you initially created. You can evaluate the design, and finally, in step 7, save it away. Now, I'll be going through these steps one at a time, so I don't want to spend too much time on my PowerPoint. Phase 2 has to do with analyzing the results. This is where you type in the data, you fit various statistical models, you decide perhaps to remove certain factors, put in quadratic terms, interactions, whatever you need, to come up with a statistical model that describes the results. Those models in step 9 can be used to find optimal settings of the factors. And finally, step 10 in the wizard saves everything away as a statfolio. Phase 3 is further experimentation. And there are a couple of facilities, as we'll see in Statgraphics, having done a single experiment to either augment the initial design or extrapolate the models outside the experimental region along the path of steepest descent. So basically, phase 1, phase 2, phase 3, and we will be going through each of these as we go through this webinar. Now, the example that I'll be using is an example from a very good book on response surface methodology. It's written by Ray Myers and Doug Montgomery. Actually, I think the second edition has recently come out with a third author. But the example I'm going to talk about and use as we go through this process today is one of a chemical process. The goal is to find the settings of time, temperature, and catalyst. Those are the 3 experimental factors that I can vary. Find the settings of those 3 factors that maximize the conversion percentage of the chemical process. Maximize the conversion percentage while keeping another response, the thermal activity, as close as possible to 57.5. It's a good example of a response surface optimization type of problem where you have 3 factors you can change, time, temperature, and catalyst, and 2 response variables, conversion percentage and thermal activity. And what you'd like to do is to achieve a particular goal that has to do with both of those responses. And this is one of the things that we made, I think, a lot easier in version 16, the ability to take multiple responses and find a good solution with respect to all of the responses simultaneously. Okay, so that's going to be our example. It's a fairly simple example. It involves only 3 factors, obviously time, temperature, and catalyst. I like to show examples with 3 factors because, well, it's easier, honestly, to show you the graphs in 3 dimensions rather than trying to show you in 4 and 5 dimensions. But the same basic principles apply if you have more than 3 experimental factors. Okay. Anyway, that's the example, and what I'd like to do now is to put my PowerPoint slides away and bring up Statgraphics. Okay. I've actually loaded Statgraphics here a few moments ago before the webinar started. This is the latest release. This is version 16.1. I'm using the classic menu. So across the top it says File, Edit, Plot, Describe, Compare, Relate, and so forth. The section I'm interested in today is the section labeled DOE for Design of Experiments. Now there are 3 menu choices on the DOE menu in version 16. There's the Experimental Design Wizard, which is where I'm going to be today, which will take me through that entire process of setting up an experiment, analyzing the results, optimizing the responses, and so forth. For those of you who are using version 15, you won't have the Design Wizard. You will have, though, menu items that allow you to create a design and analyze the design. We've also left those procedures in version 16 under the menu heading Legacy DOE Procedures, so that if you grew up or got used to Statgraphics using an earlier version, those same procedures are there unchanged in version 16. Now what the wizard that I'll be showing you today does is basically takes these various menu items and integrates it into a single window, which I hope makes it a little bit easier. Not that I think it was that difficult before, but just tries to integrate everything together. One other option on the DOE menu, Import Experiment. As we go through the experimental design process here, Statgraphics is going to create for us the experimental design. Well, sometimes people create their own experimental designs, maybe create them in Excel based upon some template they saw in a textbook or something like that. And yet they may still want to use the analytical facilities of Statgraphics. Well, what Import Experiment allows you to do is actually pull in an experiment from some external source, like an Excel file or a regular Statgraphics data file, and it'll rework it and reformulate it as an experimental design so that the wizard can then apply its various techniques to it. That's not what we're going to do today, though. We're going to today select Experimental Design Wizard, which is the version 16 integrated process that allows you to go through the whole setup and analysis of an experiment. Now, when you select the Experimental Design Wizard, it'll pull up a menu. Pull up a window, a new window. And we will be, as we go through the entire process now, within this single window. Along the top of the window is a special toolbar that has 12 steps. It's a 12-step process, the way we've developed the wizard, starting with the definition of the experiment all the way through step 12, which is extrapolation of the results to try to predict where you might do even better than you saw during the experiment. What I want to do today, though, is take that example from Myers and Montgomery and show you how the whole process works. Well, we might as well begin with step 1. Step 1 asks you to define the response variables. Now, the response variables are going to be the variables that you measure as a result of the experiment. Okay, they're the responses. The things like strength or purity or a dimension or something like that. Typically, responses are the things that you want to optimize. Now, the way the dialog box is set up, it starts and it asks for a comment. So I'll just put in perhaps RSM, Response Surface Method Example, as my comment. It also wants you to specify how many response variables you will be measuring every time you do an experiment. Now you can specify from 1 to 16. In our case, there are actually 2 responses. There's the conversion percentage, the percent of the raw material that was converted during the chemical process, and secondly, the thermal activity. Now, I need to put in a name for each of these, so I'm going to put in for the first, conversion. This will end up, incidentally, being a column in our spreadsheet, so it's nice if you label it in a way it will be easily recognizable. Together with the name, we also have the units, and in this case, conversion will be measured as a percentage. The second response of interest is the thermal activity. Okay, and it would be nice if I spelled it right. Thermal activity. And I'm not sure what the units of that are, so I'm just going to leave that blank. Now, the way this all works is you put in each of the response variables you're going to be measuring. You then move over to the pull-down list under Analyze and tell it what you want to analyze. What are you going to build a statistical model for? Well, usually it's going to be for the mean. I'll be interested in modeling mean conversion as a function, in this case, of time, temperature, and whatever my third factor was. However, I could also build, if I wanted to, a model for the standard deviation. In this case, I want to actually maximize the mean conversion. But you can understand in other experiments you might want to, for example, minimize the standard deviation of some critical quantity. So you can specify as a response the standard deviation of a response, or the CV, that's the coefficient of variation, standard deviation divided by the mean. We also allow you to choose any of the 4 Taguchi signal-to-noise ratios if you're a fan of some of those. In this case, though, I'm going to just keep it at the mean. I'm going to be modeling mean conversion and mean thermal activity. Okay, well, I also need to tell it what the goal is. Is it to maximize that response? Is it to minimize the response, or to hit a target? Well, let's see. I want to maximize percent conversion. I want to hit a target for thermal activity. And the target for thermal activity was 57.5 in the example we want to talk about. Okay, so this is setting it up for the optimization, you see, that I'm going to do later on down the road. Okay. Now, there's also a field on the initial dialog box labeled impact. This has to do with the relative importance of one response versus another. And you can specify any number between 1 and 5 to identify how important one response is versus another. Now, they're initially both set to 3. And it's really the relative magnitude of those numbers that matter. Since they're both set to 3, they'll both be treated as equally important when it comes to the optimization phase. But if you thought, for example, that conversion was much more important than thermal activity, you could assign a 5 to conversion and a 1 to thermal activity. And when it does the optimization, most of the weight would go then to trying to maximize the conversion, and only a little bit to trying to be close to the target on thermal activity. Well, I had it set to 3 and 3, making them equally important. This doesn't always matter, by the way. You may often get the same solution regardless of how you change the impacts. But if the process is such that there's a real trade-off between the responses, if you can't achieve good conditions on both simultaneously, then the relative impact can make a difference. No. All right, 3 more fields that have to be set out: sensitivity, minimum, and maximum. These three fields have to do with, again, the optimization on down the road. If I'm trying to maximize something, then minimum and maximum are the settings for the acceptable range or acceptable values of that response. Now, a conversion percentage can't be any more than 100, so if we get to 100, that's great. If I put in a number like 80, though, for the minimum, I'm telling it basically that anything below 80 is entirely unacceptable. Technically, what the multiple optimization procedure does is it defines something called the desirability of a particular response value. And I'm telling it that anything less than 80 is completely undesirable. It gets a desirability of 0. Whereas 100 gets a desirability of 1. And if you read a little bit in our documentation about desirability functions, they basically defined as going from 0 to 1 on each of the variables. For conversion, I'm saying anything 80 or below gets a 0, anything 100 or above gets a 1, because that's as good as you can get. Now, with respect to the thermal activity, the target is 57.5. So that if you're right on target, that's perfect. That'll get a desirability of 1. In this case, you need to specify minimums and maximums below which it's unacceptable and above which it's unacceptable. So I'll put in a 55 and 60 as the acceptable range of thermal activity. Anything outside that range gets a 0 for its desirability. And starting at 55 and 60, going in toward 57.5, the desirability will then go up. Now, you also see something called sensitivity. Sensitivity tells it how important it is to be close to the optimum over this range. It's actually easiest to understand with something like thermal activity. Right now it says the sensitivity is medium. That means that the desirability of a response basically varies in a linear fashion between the minimum and the target. If you don't much care where you are within the range 55 to 60, you can say I'm not really sensitive to very low sensitivity, which means anywhere between 55 and 60 is pretty much equally good. On the other hand, if you really, really, really want to be close to 57.5, you can set it to very high. Okay. Usually, I just leave them at medium, but if I really, really, really wanted to force it close to its best condition, I could set it to a higher level of sensitivity. Anyway, that will define the two responses in this case. So I'll just go ahead and press OK. And as I go through the steps here in the Design of Experiments Wizard window, the information will pop up and be summarized. Okay? All right. On to step 2. Step 2 has to do with defining the experimental factors. Now, in Statgraphics, there are 3 different types of factors that you can change during the course of an experiment. First off, there are controllable process factors. Okay, these are the typical types of factors like time and temperature, amount of catalyst, and so forth. Things that you can normally control and what you're going to be wanting to find perhaps the optimal level of. And in this case, that's what we're going to have. We're actually going to have 3 controllable process factors. You could also, though, specify as part of the design controllable mixture components. Okay, mixture components are components of a mixture. If you have sort of a blending problem. For example, we have a rocket propellant example in our documentation where a rocket propellant is a certain amount of fuel, a certain amount of binder, and a certain amount of oxidizer. And with mixture components, you change the relative percentage of components in the mix. Now, I'm not going to have time to talk about that today, but you can add mixture components also. You can also add to the design noise factors. Noise factors are factors that normally you could not control. Things like relative humidity, variations in raw material, things like that. And robust parameter designs, which I'm going to talk about in a future webinar, look for settings of the controllable process factors that minimize the effect of the noise factors. Robust parameter design, looking for robust operating conditions where the noise has little impact on the response. Now, we're going to have to keep it simple today, so I'm going to keep it and talk about just process factors. And there are going to be three process factors. The first process factor is going to be the time that I let this chemical reaction run. It's going to be measured in minutes, and you can see here that I have a choice. I can specify that a factor is categorical or continuous. Continuous means it takes values over a continuous range, which is what we're going to have here. I'm going to tell it that I'd like to experiment over a range of, let's say, 10 to 15 minutes. And if it's a continuous variable, anything between the low and the high is a reasonable setting. On the other hand, some factors are naturally categorical. And if you want to put a categorical factor in, you do it by actually going over to the levels field here and specifying levels for the categorical factor. So I could put, for example, low, comma, medium, comma, high, specifying through just 3 levels of the factors, and those would be the only allowable levels for the factors. And you can combine categoricals and continuous in a single design. In this case, my factors are actually all going to be continuous. So I'm going to have time in minutes. I'm going to have temperature. Let's put this one in degrees centigrade. And in the example, they decided to let temperature range between 170 and 200 degrees. The third factor was the percent of catalyst. So it's catalyst as a percent. Also a continuous factor running between 2% and 3%. Okay. Now, the design can contain up to a total of 26 different factors. I think it's limited to a maximum of 16 of any particular time, but a total of 26 factors. We're not going to do anything nearly that complicated today. I've just picked 3: time, temperature, and catalyst. All right, let's press OK. It's now added that information, as you can see, to the experimental design window. Okay. Step 3, once you've defined the responses, defined the experimental factors, it's now time to select the experiment. And when I press the Step 3 button, a dialog box will come up and will allow me to specify the types and select the type of experiment that I want to run. Now, depending upon what type of variables you have, process variables, mixture components, noise factors, and so forth, you may need to specify up to 3 different segments of your design. Since I only have process factors here, there'll only be one segment. But if you had other types of components, you may have to pick a different type of design for each set of factors. To set a particular design, you push the Options button. Now, for continuous factors such as I have now, I'll get a dialog box allowing me to pick from 4 different types of designs. I can pick from a screening design. That's basically a 2-level design that lets me run each factor at a high level and a low level, with the goal of, in a screening design typically, of finding the most important factors. Now, screening designs are often done on 7, 8 factors at a time, where you may have lots of things you'd like to change. You're not sure what's most important, and you don't want to spend a whole lot of money just finding out what's important and have nothing left for the optimization process. They contain factorials, fractional factorials, Plackett-Berman designs, things like that. What we're going to want to do here, though, is slightly different. I'm going to select, in this case, a response surface design. These are optimization experiments. These are things like Box-Benken designs, central composite designs, designs like that, intended to find the optimal conditions of the factors. We also have choices, multi-level factorial. That's usually used if you're going to do a d-optimal design. And then there's orthogonal arrays. These were developed by Professor Taguchi. They're like L3s, L9s, things like that. Okay. We're going to stick with the response surface design today because I want to do some optimization. Okay. Now, when you pick the type of design that you want, an additional dialog box will pop up, giving you a choice of different designs for that number of factors. It knows now, for example, that I've picked 3 continuous factors. So it's going to offer me things like a Box-Benken design, a central composite design, a 3-level design. The one we're going to do is actually going to be the central composite design. This consists of a 2-cubed factorial, which is 4 points, high, low, high, low, high, low. That's actually 8 points. It's all combinations of high and low for my 3 factors. Plus a star, which you'll see in a minute, is points through the centers of the faces of the cube. It's a great design, relatively small number of runs. You can see here the default is to run 16 runs, with a reasonable number of degrees of freedom left to estimate the error. Okay, it says that this will be designed with 16 runs, and there will be 6 degrees of freedom to estimate the error. Now, we need an estimate of error in order to know what the noise is in the experimental process. I usually recommend at least 3 or 4 degrees of freedom for the error. This one would have 6, so that would be fine. Okay, so anyway, I'm going to pick a central composite design. Now, when I pick a central composite design, I'm going to get a few options. Okay, there are rotatable central composite designs, orthogonal CCDs, rotatable and orthogonal, face-centered, a lot of different design options. Okay, too many to talk about today, so we'll just take, and this is usually a good rule in Statgraphics, take the defaults if you're not sure what you want to choose. I can also specify the number of center points in the design. Center points are points, experiments, at a middle level of all of the factors. For example, I'm going to be experimenting, I believe it was between 10 and 15 minutes. 10 is my low, 15 is my high, 12.5 minutes would be the center point. And it's usually a good idea as you do an experimental design to do several points right in the middle of the experimental design region. And you can see that by default, it's offering you, suggesting you do 2 center points. Now, to reproduce the Myers and Montgomery example, however, I'm going to change that to 6. They actually did a total of 20 runs. You can see the number of runs changes at the top. I've added 4 additional center points. Why'd they do that? Well, probably to get a better measure of the experimental error. So that's actually one set of conditions done 6 times. And as you look at the variation among the 6 responses, you'll get a good idea of the error. Now, you have a choice also as you do this of whether you want to randomize the design or not. I usually suggest you do, but if you want to reproduce the results I have in this class, you'll turn off the randomized flag. That's just to make sure we all get things in the same order if you're trying to reproduce things with me here. I also have a choice of where to put the center points, and for the example, I'm going to ask it to put the center points at the end of the list. Again, normally I would like to randomize things, but just for purposes of the experiment, of the webinar here, it's a good idea, I think, to to go ahead and not randomize it. So you'll have it in what's called standard order. All right. Once I select those options, it will then add to the original dialog box here a list of the runs that it will want me to do. Now, what it wants to do in this particular instance is run 8 runs, runs 1 through 8, which are a 2-level factorial. High, low, high, low, high, low, all combinations for time, temperature, and catalyst. It then wants to run in the CTD 6 runs, which are, I think I just closed off one of the runs. Yeah, couldn't see it there. Okay, 6 runs, that's runs 9 through 14, which are star points. Star points are at a center value of 2 of the factors and an extra low or extra high setting for the third. So it actually says I want to run at 8.29552 minutes at 165 degrees and the catalyst at 2.5%. We'll get a chance in a moment to round those off to something more reasonable. What it does, though, is it creates what's called a perfectly rotatable design. So it gives you these really sort of what look like crazy settings, but we expect you to round those off a little bit to something more reasonable. Okay. Up here is one other field I need to show you, samples per run. In this case, I'm only going to take one measurement from my chemical process every time I do an experiment. It's not uncommon, however, once you set up an experiment, get each one of these 20 runs now to take maybe 30 measurements. And if you want to, here you can tell this program that every time I do a run, I'm going to do 30 samples. And unlike version 15, where you'd have to, for every run, compute the means yourselves, version 16 will allow you to put in 30 results for each run, and it will automatically compute the means and the standard deviations. Okay. Well, if I press OK now, what it'll do is select this run, add this design, add some information to the DOE window, and at the same time over here in the data book, you can see it's put in the 20 runs that it wants me to run. Now this is where I can come and round things off a little bit. You can see down here in row 9, it's asked me to run for 8.29552 minutes. I can just change that to 8.3, change this one to 16.7, maybe change this to 160, this to 210. It gave you what was called a perfectly orthogonal rotatable design in this case. But if you look in Myers and Montgomery book, you'll see that they rounded it off a little bit. General rule in Statgraphics is that when it comes time to analyze the data, we'll analyze whatever's in the window, the data sheet window, regardless of what we initially set up. So I just rounded it off a little bit. So there's the experimental design that I want to run, and now I've rounded off the settings a little bit. Okay. All right, so that takes me through the first 3 steps. Let me quickly show you a couple of other steps before we go ahead and analyze the data. Step 4, specify the model. Step 4 allows me to specify a particular type of model. Either a model that just involves a mean, a model with just main effects, a linear model, maybe just time, temperature, and catalyst, a model with 2-factor interactions as well as main effects, a quadratic model, or even a cubic model. What this will affect is some of the diagnostics that the program generates so that you can assess the properties of a particular design. This actually doesn't have any effect on the analysis. You can specify the model later on when the models are fit, but it does affect the diagnostics. Now, the typical model for a response surface design like this has main effects, interactions like AB, AC, BC, and also quadratic terms like AA, BB, and CC. Okay, so the defaults here were fine, but for purposes of diagnostics, you could have selected something different. Yeah. Okay, that was step 4. Step 5, select runs. Now, this is only necessary if you intend to do a de-optimal design. In a de-optimal design, the way Statgraphics does it, we have you generate a large number of runs, typically. And then we ask the program to pick out a subset of the runs. For example, here's a list of all the 20 runs that I'm going to do. Let's suppose, though, that these runs were really, really, really expensive. Okay, and I wanted not to do all 20, just to do 13. And you can see down here, I can specify the number of runs desired. Why 13? Well, there are actually, as it says, 10 coefficients in the models that I want to fit. If I put in 3 to measure experimental error, that means I really don't want to go any less than 13. It sort of depends how much you want to spend, though. If I wanted to, I could have the program select 13 runs. And if I push the button here that says select runs using backward algorithm, it's now selected what's called a de-optimal design. That is a design that will, in a particular way, give you the best estimate of your mathematical models, given the number of runs that you want to do, like 13 runs. And it's actually highlighted in red here, the best 13 runs to do. And there are some measures of what are called design efficiency, which I don't really have to go into. What it's done, though, is it's tried to find the design with the highest D efficiency, and it found one with about 65% in this case. Well, that'll be a topic of another webinar. I'll show you how to really use these de-optimal designs. For the moment, I'm just going to cancel that to keep the 20 runs that we initially set up. Okay. Well, step 6, evaluate design, gives me a number of different options that I can now use to assess the properties of this particular design. Things I'd like best are typically things like the ANOVA table, the correlation matrix, perhaps a plot of the design points. I'm going to select some additional output, and it'll add now to the Experimental Design Wizard window some interesting information. Now, one interesting information, of course, interesting plot, is a plot of the design. This is the central composite design in the space of time, temperature, and catalyst. This is the design I'm going to run. It consists of 8 points at different combinations of the original highs and lows of the different factors. It has a center point in the middle of the design, actually a replicated center point. And then the star points are these triangles here located out through the faces of the experiment. This is a nice plot showing you what the design is in the space of time, temperature, and catalyst. Okay. Additional output that it shows over here, it shows you the ANOVA table. It shows you that there are 9 degrees of freedom being used to fit the statistical model. 10 degrees of freedom left for experimental error, 5 of which are pure. Pure means they're from replicates, and because we're going to replicate the center point 6 times, there are 5 degrees of freedom for pure error. 5 left behind to estimate lack of fit, to tell me whether the model that I fit And in this case, it assumes you're going to be fitting that quadratic model. Remember I specified quadratic before? There'll be 5 degrees of freedom left to tell you whether the quadratic model is good enough. So that's a pretty good setup. I've got 5 degrees of freedom left for pure error, 5 degrees of freedom that I can use to tell me whether the model is good or not. A more complicated model, incidentally, would be the cubic model with cubic terms, but I'm initially not going to assume that. Down here, it also shows me the correlation matrix. This shows me whether there's any confounding between the different effects. It shows me for each of the main effects, the quadratics, and the interactions, whether things are orthogonal. And if it was perfectly orthogonal and have a 1 down the diagonals and 0 elsewhere, or whether there is confounding. Well, in this particular design, because I picked a rotatable central composite, there's a small amount of correlation between the quadratics. For example, AA, which is time squared, and BB, which is temperature squared. So small, though, it's going to have very little impact on any results. But if you want to assess the properties of the design, you can look at that correlation matrix. Okay. Well, there are a lot of other things I could choose as well, other diagnostics, but I'll have to save that for an additional webinar because I want to get off and analyze some data. So let's go ahead, having set up the design now and saved the experiment. Experiments, incidentally, are saved in files with an SGX extension. And I might call, for example, this particular experimental file Wednesday. It'll be saved as wednesday.sgx so that it can be loaded later on. So I'll just go ahead and say save, and it's now saved that particular design away. Well, at that point, you have your experimental design created. Your turn. Go off, do the experiments, and when you're done, come back and type in the values that you got for each of the runs for conversion percentage and thermal activity. Now, in order to save some time, I'm not going to type in all the results. Let me choose File New, and just clear this off to an empty data sheet, because I've already saved the data. So let's go ahead. Let me go to File, Open Data Source. And I do have a Statgraphics data file already saved away. Here it is, Conversion and Activity, that has the results already typed in. It's in a file, and this is provided, incidentally, in a link on our webinars page, so you can load this file and play around with it yourself. It's in a file called conversionandactivity.sgx. When you load an SGX file, it at the same time recognizes that it was created by the Experimental Design Wizard, so as it opened that file, it also created the Experimental Design window. And now, because there are data in the response columns, Step 8 will allow you to analyze the data. If I press Step 8, it will now go ahead and fit mathematical models for me. Now, one thing it's going to want to know as it fits the mathematical models is whether or not I want to transform any of the response variables. If you've done a lot of data modeling, you know that often by taking a square root or a logarithm or reciprocal or some other transformation, it's possible to simplify the mathematical models. You know, it's very common, for example, to go ahead and fit a model for log conversion, perhaps. Okay, so you can, if you want, at this stage, tell it to build a model for transform data. Now, I'm not going to transform either of these variables, but it is an option as you start the analysis. Okay. If you decide just to take the data as is, you can press OK. And what will happen is it will now open up two additional windows. One, oops, I have to respond to this. It just tells me that it's fit the data here. I need to press OK. It's actually created two new windows now. One, fitting a model for thermal activity. A second, fitting a model for conversion. Okay. In version 15, incidentally, you'd have to go to the main menu and analyze conversion, then go back to the main menu, analyze thermal activity. With the Design Wizard, it just automatically takes all the variables and opens up an Analyze Experiment window. Now, there are a couple panes in these experimental design windows that are quite important. For example, I'm looking at Analyze Experiment Conversion, and down in the bottom left, you will see what's called the Analysis of Variance. The Analysis of Variance table will show you each effect in the mathematical model. Now, by default, if you fit a response surface design, there'll be terms for the main effects. These are the average effects of time, temperature, and catalyst. There'll be terms like A, B, A, C. Those are interactions between pairs of factors. And there'll be terms like AA, oops, where is it? AA here, BB, CC, which are quadratic effects. In an ANOVA table, if the p-value is less than 0.05, then the factor is statistically significant at the 95% level. And you can see the Statgraphics has labeled in red all effects with a p-value less than 0.05, which means there are actually three terms in my mathematical model: time here, time squared, and time interacting with temperature, the AB interaction, which are actually not statistically significant. Now, that's the ANOVA table. The same information is also given in the standardized Pareto chart. The standardized Pareto chart will show me from most important to least important the magnitude of each of the effects. And it's actually drawn showing the standardized effect along the x-axis. Well, the standardized effect is equivalent to a t statistic. And the larger the t, the more significant the effect. So of all the effects, actually the AC interaction is the strongest, followed by the catalyst effect, followed by a quadratic term on catalyst, and so forth. Anything to the right-hand side of the vertical line is statistically significant at the 95% level. Anything to the left-hand side is not. So you can see, again, same information as in the ANOVA table. A, AB, and AA do not add significantly to my model. Okay, now, in doing statistical modeling, a lot of us believe in what's called the KISS principle. KISS stands for Keep It Simple Statistically. And the basic principle is that simpler models are usually better models. Models with fewer coefficients usually are easier to interpolate, give me more reliable predictions, and so forth. So if I see mathematical models that have insignificant terms, I like to remove them. So, for example, this AA term, I'd like to take it out. AB, I'd like to get rid of it. A, well, there's one caveat. As we remove terms from a statistical model, we typically don't like to remove lower order terms if they're contained in higher order terms that we're going to keep. So, for example, look at time. Time is clearly not significant. However, time is involved in a significant interaction with catalyst, AC. So most of us would prefer not to remove time. Now, AB and AA we can remove. They're not involved in other significant effects. But A is a part of a significant effect, so typically it would not be removed. Now, how do I remove them? Well, I actually push the right mouse button, very important option in Statgraphics, pushing that right mouse button. I go to Analysis Options and push the button on the right labeled Exclude. This will give me a list of the effects, and then I can take effects like AA, double-click to exclude it. AB, double-click to exclude it. If I then press OK and OK, it's now cut my mathematical model back to a model involving just 1, 2, 3, 4, 7 effects, which I would tend to believe would then be a simpler and more usable model. Okay. Incidentally, if you wanted to see the model, if I go to the Tables and Graphs button on the Analysis toolbar, there's another table, Regression Coefficients. And this will actually show you down in the Stat Advisor section what the mathematical model is I've been talking about. What it is, it's a mathematical model relating conversion to time, temperature, and catalyst, with cross products for the interactions and quadratic terms for things like a squared, b squared, and so forth. Okay. So there's a mathematical model for conversion. Now I need to do the same thing for thermal activity. So let's go back here to thermal activity. Let's take a look at the standardized Pareto chart. Okay, well, let's see. Time looks to be significant. Catalyst looks to be significant. AA, almost significant. Actually, let me look at the ANOVA table for a moment on AA. Here it is. It actually has a value of about 0.10. Significant, practically significant at 90%, but not at 95%. Well, these guys can all go. Everybody else, I tended, whenever I looked at this data, to leave AA in, but that's sort of your choice. Anyway, let's simplify this model. Let's right-click, Analysis Options, Exclude. And in this case, let's take out everything except AC and AA. Whoops, that's wrong. Let me put that back. Right? AC and AA. Okay, okay. Oh, look at that. Now when I take the little guys out, AA actually sneaks over the line and becomes significant. So anyway, basically I now have, I think, a pretty good model for both thermal activity and conversion. Okay, so I've got my models. Let's go back to the experimental design wizard. And incidentally, once you've done the analysis, it'll give you a summary of the models down here, how many terms they have, what the R-squareds is. And you can see I've got about 88% R-squareds now for each of those variables. Time to do some optimization. Let's go up to where it says Step 9 and press the button. Step 9, Optimize Results. What responses do you want to optimize? Well, you could actually choose to optimize either one separately, but my whole goal here was to optimize the two together. So I'm going to set it to conversion, thermal activity, press OK. Now, the optimization is a search, and it'll actually start at one or more starting points to try to find the global optimum. Now, by default, it'll start from the predicted design point. I usually like to start it everywhere, though. Tell it to search from a bunch of different points and find the overall best set of conditions. If I do that and I press OK, there we go. Responses have been optimized. Desirability at the optimum location equals 89.86%. Now, that refers back to the way I defined the desirability functions on that very first dialog box. I told it that 80 to 100% was where I wanted to be on conversion, 55 to 60 on thermal activity. And basically it says it's been able to get to close to 90% overall desirability. Now if I press OK, it will have added to the design window down here what the optimal settings are. It says to optimize your process, you should run at 11.2 minutes at 210 degrees with about 2.3% catalyst. Up here it will show you what that will achieve. It will achieve approximately a 96% conversion and actually hit 57.5 exactly with respect to the thermal activity. Okay, so it's been able to get thermal activity right where it wanted to, and it's been able to find a location, and this is incidentally optimized over the experimental region. It's been able to find a location in the experimental region where it could get 96% conversion. Now, it's often nice to see this, of course, and if I go back to step 6, if I actually go back to step 6 where it says evaluate the design, there are a couple plots, additional plots on step 6 that are quite useful once you fit a model. One is called the desirability plot, and one is called the overlaid contour plots. Now let me show you these two. Okay, the first plots the desirability, and it's done it here actually as a three-dimensional plot. Here it's plotted as a function of time and temperature. Those are two of my factors. With catalyst, you can see at the top, held at 2.3. That was the optimal location. The desirability at a particular location. Now, desirability goes on a scale of 0 to 1. And it said we were actually close to about a 0.9 or 90% desirability. And it actually shows me where in the experimental region, at least with respect to time and temperature, I can achieve desirable results. Well, the best results, best desirability, highest desirability is up there at high temperatures and relatively short times. The height of the surface here actually represents the desirability, and you can see that the surface is highest in the back. There's also a secondary optimum at lower temperatures. You can see it's actually going back up again at lower temperatures. I'm not sure why that is. Probably just an part of the mathematical model, because we are just using polynomials. But clearly, the best conditions are back here. Now, this is a plot of where to operate the process with respect to time, temperature, with catalyst held fixed. If you want to see it with respect to all three of my factors, I can right-click, go to Pane Options, and ask, in this case, for a 3D contour plot. Now, a 3D contour plot, you'll see what it is in just a moment. I'm going to ask for a 3D contour plot with continuous contours. This is going to draw a plot showing me the desirability of operating at a particular point in my experimental space. Now, with respect to all three of the factors. This now is the time axis, this is the temperature axis, and the vertical axis now is catalyst. That's my third factor. So basically everywhere within this cube is a place that I could operate my process. Desirability is now shown by a color code. Blue, not very desirable, up to red, very desirable. And what it's done is it's done a slice, actually. It's at the optimal catalyst 2.32. So that this point right back here is actually the optimum point in the space of time, temperature, and catalyst. Now, there's a nice new feature also in version 16 of Statgraphics, though, something called the Response Surface Explorer. if I push this rainbow-looking button up here on the analysis toolbar, this will open up a floating dialog box. The floating dialog box allows me to grab any one of those variables and change it. In particular, I usually like to grab the catalyst. And if I grab the catalyst, I can change it. I can lower it and increase it. And you can see that actually the optimal time and temperature depend upon the catalyst that I'm going to use. The optimum catalyst, it says, was around 2.3, right around here. And that little square is the optimum point. If I go higher, though, you see I'd want to go for a shorter time. Or if I lowered the catalyst, I'd want to go for a somewhat longer time. It's called a response surface explorer. It allows you to explore how the desirability varies throughout that entire three-dimensional space. A nice feature, I think, that we've added to version 16, which allow you to basically explore that mathematical model. Okay. Well, let me put the Explorer away, and before I do anything else, step 10 says save the results, which allows me to basically save everything I've been doing in a stat folio. Okay. All right, two more things to show you, and then I'll take a couple questions. First, augment design. If I've created an experimental design, for example, I've created this design with 20 experimental runs. Okay, I can, if I like, add additional runs to the experiment. There is a button on the toolbar labeled Augment Design. And if I push the Step 11 Augment Design button, a dialog box will come up, which will allow me to add additional runs to the designs. Now, there's not much you can do to a response surface design. This is already fairly complete. The only option it's going to allow me is to add some replicates. If you were doing a screening design, though, if you'd done a fractional factorial design, for instance, then there are a lot of other options. Add a fraction, clear main effects, clear a factor, add star points, which will actually add additional runs to the design to bring a, what might be called a resolution 5 design, which is something that has to do with screening, up to a resolution 4 or resolution. Brings a 3 to either a 4 or a 5. Some examples of that in our documentation on screening designs. Again, more than I can talk about today. But there is an option, Augment Design, that will add additional runs to certain types of experiments. And finally, there is an option to extrapolate the results of this experiment. Now, the experiment here was within a particular region. It was in a particular region of time, temperature, and catalyst. Having built a mathematical model, actually two, one for conversion, one for thermal activity, it's often good to be able to predict the results outside the experimental region. And Statgraphics will extrapolate the mathematical models outside the extrapolation, the original region from a particular point. So, for example, I'm going to tell it right now, take the best predicted design point, okay, and extrapolate outside the experimental region. Tell me where you think mathematically, now we never know for sure, but where you think mathematically we might get the best results. And extrapolate it in steps of 1% desirability. You may remember the best design point's about 89–90% desirability. Find me where I might get 91%, 92%, 93%, and so forth. And if you pressed OK, oh, it didn't like something. Oh, it didn't like this. When you do this, you also tell it the region over which you want to extrapolate. Right now, I've got the entire experimental region, 10 to 15, 170 to 200, 2 to 3. It wants me to expand the experimental region. Well, let me expand the experimental region, at least with respect to temperature. Temperature, I know, was constrained. If you remember, the optimum was 210, which was right on the boundary. Let me set it to 250. Okay. There we go. And now what it's done, if I go back here and go down to space 12, it's found certain combinations, okay, where I can increase the desirability. Okay, and if you look at these steps right about here, okay, it's been able, this is the estimated desirability, to find a location, okay, with about 99% desirability. It says that that is, incidentally, what is that? That's step 32. These are all points along the path of steepest ascent. Okay, that's at a time of 11.23 minutes, 213.5 degrees, and 2.3% catalyst. So basically what you can do with the extrapolate feature is you can take a particular starting point. Okay, and I noticed incidentally in this case I started from the center of the experimental region. I thought I was going to start from the middle, from the best design point, but I must have told it to start from the center of the experimental region because it started at 12.5, 210, and 2.5. And in the center of the experimental region it actually got only a desirability of about 12%. And following what's called the path of steepest ascent, it moved all three of the variables up to new levels at which it predicts the desirability would go to 0.999. When you do the extrapolate, you can extrapolate from various points, the center of the design, the best observed design point, the best predicted design point, the best predicted vertex, extrapolate from different points. Okay. And so it's decided that if you were willing to bring the temperature to 213.5, which is outside the design region, it thinks you can do even better than what you saw in the experimental design. Okay. Well, as you can see, there's lots and lots and lots of fun stuff in the Experimental Design Wizard. I have put together a PowerPoint that you can also download from our website, summarizing some of the things that we did. As you can see, there's a 3D contour plot during the talk. Some of the things I didn't fit into this, and I do apologize for going a little longer than the hour I anticipated. Some things I'm going to have to save for the future. One is robust parameter designs. Robust parameter designs are designs where you're looking for robust operating conditions, conditions where noise factors don't have much impact on process factors. Designing designs with both process and mixture components. De-optimal designs, which can be used to, for example, fix the botched experiment, where someone has gone out, done an experiment without planning it out ahead of time. De-optimal designs are a good way of trying to improve the properties of some design that's already been done. Any more information, you can find it at www.statgraphics.com. Send an email if you'd like to info@statgraphics.com, and we'll try to respond to those. Okay, I thank you for your patience. Let me see whether there are any questions that have been submitted during the talk. Let me pull up my screen here. Chat. I do see a couple questions. One had to do with the design itself, having to do with what were the triangles back in the original design. Let me see. I think I have a slide actually in my PowerPoint. There it is. It had that original design on it. Each of the points on the on this particular plot is a place where I'm going to collect data. We have just distinguished with different symbols what are called the factorial points, which are different combinations of the highs and the lows. Those are the vertices of the cube. We have, I guess, little diamonds for those. A circle at the center of the design and little triangles out at the star points. In a central composite design, you actually collect data at a point where you hold any two factors, let's say time and temperature at their middle levels, and then go out through a face, for example, through the top face, to a value of catalyst somewhat higher even than you had specified as its high level. So I think of these as extra low and extra high values of a particular factor like catalyst. They're called star points because if you connect these up, it sort of looks like a star. Okay, someone also suggests that it would be nice to be able to transform the experimental factors as well as the response. Okay, that has to do with when I fit the mathematical model, we gave you a dialog box and you could pick the log and square root and so forth to automatically transform the y variable, the response variables. But the x variables are in the mathematical model untransformed. Someone would like to be able to transform those as well. That's a good idea. Never thought of that. Are there any plots to see extrapolated results? No, actually there aren't any plots right at the moment that show the extrapolated results. I'll have to write that one down also for the a future version. What you could do, though, I mean, one of the features of Statgraphics is that these tables are real tables. I can go, for example, here to the settings of the experimental factors in any one of these tables. I can grab this value. I can just take these numbers, go to, for example, Control-C to copy them to the Windows clipboard, and then quickly call up, for example, Excel. Okay, where's Excel? There it is. And let me see what happens. Yeah, okay, there I pasted the results into Excel. And I could also do that. Here is the desirability and so forth. So I could copy those, paste them into Excel. Okay, now I've got everything in Excel. In Statgraphics, I could now close things off, get myself an empty data sheet, go back to Excel, grab the data, copy it to the clipboard, come back to Statgraphics, paste it in. And as I paste it in, I'll tell it has just column names, and there's my results. So let's do something perhaps like an XYZ plot. Let's see, maybe take time, temperature, time here, temperature here, desirability here. Let's see what I get. Okay. Well, there's a plot of the extrapolated results. Temperature, oh, I put temperature and temperature. That's not what I meant to do. I meant to put time and temperature. Okay, here is actually what happened on the path of steepest descent. This is sort of interesting. At least with respect to time and temperature, it started at the center of the experimental design, which was 12.5 time, 210 temperature. Decreased time, increased temperature slowly, and the desirability went up. It then looks like it hit a limit below which time, reducing the time anymore was not going to help, so it then went ahead and increased the temperature. Okay, since this is a question, let me do one more thing. Let me do a multiple XYZ plot. Let me take time and temperature again. Let's take, though, conversion, put it on a left axis, thermal activity, put it on a right axis. Let's see what this looks like. Oh, okay. I've now showed you what happens as you move along the path of steepest descent. What happens to the conversion? The left-hand axis here is conversion. So as I move along the path of steepest descent, conversion goes up, thermal activity goes down. This is the thermal activity axis over here. So on respect to thermal activity, we started here and it went down like this. With respect to conversion, it went up like this. So at the end, and the last point there, at the end, it had hit the optimal thermal activity of 57.5 and gotten conversion almost all the way up to 100. Long answer to a simple question. There's no built-in features, but you can save those results and use some other procedures in Statgraphics to go ahead then and plot what happens. Are all the here's another question. Are all the Wizard features on version 16 available manually on version 15? No. Most of them are. Some of them aren't. Particularly things like those three-dimensional plots with the Response Surface Explorer was not in version 15. Also not in 15 was the ability to add process factors with mixture factors. With respect to what we did today, though, pretty much everything could have been done under version 15. The one thing that would have been a lot harder would have been the multiple response optimization, though. Because in version 15, you'd have to go to the menu, build the model for conversion. Go to the menu again, build the model for thermal activity. Then go to another menu item to do multiple response optimization. So it could have been done, but it would have been a lot more work. 6, can you see the predictions and confidence values for added values of factors in the data matrix? That's a good question. I didn't show that, but the answer to that is yes. Let me bring up the Statfolio for the original design. Okay. All right. Here is the original design. It has 20 runs. Okay, and if I go to the Experimental Design Wizard, one of the windows in the Experimental Design Wizard is a desirability window. See, there's an option for desirability. This will actually take each of the runs in the experiment. Here are your 20 runs. show you what the observed conversion was, what the model would have predicted. Show you what the observed thermal activity was, what the model would have predicted. Show you what the observed desirability is, what the model would have predicted. Okay? So it actually gives you a table of what happened at those 20 runs. Now, there's a feature in Statgraphics that applies to the experimental design procedures, the general linear models procedure, the multiple regression procedures, and so forth, is that you can put in an additional run. You can, for example, go back to the data sheet here, put in an additional run. Set your own time, temperature, and catalyst. So, for example, put in 11 minutes at 213 degrees, 2.3% catalyst. If you leave the response columns blank, don't put anything in for the response, then it can't be used to fit the mathematical models. However, it will add, as I remember, yes it did, an additional row to the bottom of this table showing me what the predicted conversion would be, the predicted thermal activity, and over here what the predicted desirability would be. Now, where was this? Well, this was under step 6. It's a table called desirability. After you've already done the experiment, you fit the mathematical models and so forth, and you're happy. You go back to the design, go down to the bottom of the data sheet below all the experimental runs, and put in as many different combinations of the factors as you want. Leave the responses blank, and it will know to add additional rows to the bottom of this table showing you the predicted values, including the desirability. So the answer to that one was yes, it is possible to do that. Can you describe the Analyze tab again in the Define Response window of the Wizard? The Analyze tab again in Define Responses. Let's go back to Define Responses again. Oh, the Analyze tab, yeah. The Analyze tab lets you specify the quantity for which you want to build the mathematical model. In most design of experiments, we're building mathematical models for the mean, as I did here. How does the mean conversion vary as a function of time, temperature, and catalyst? In other cases, you might actually want to model the standard deviation. Now, you remember before I told you that one of the options when you created the design was to take multiple samples during each run of the experiment. If you wanted to analyze, for example, the standard deviation, and I didn't make this point clear, which is probably why it's confusing. If you really want to model how the standard deviation changes as a function of time, temperature, and catalyst, what you can do is run this exact same design, but every time you do one of the 20 runs, get 30 different samples of your product. Measure the conversion or the thermal activity 30 times and calculate the standard deviation. It's headed off toward those RPD designs that I was talking about, those robust parameter designs, where what you're often interested in is not only maximizing conversion, but getting to a place where conversion won't vary much, for example, from one batch to the next, to the next, to the next, or one day to the next, to the next, to the next. So at the same time that you're trying to maximize the mean conversion, you might also be trying to minimize the standard deviation between batches. Now, you can only model that if you take multiple samples during each run. So imagine yourself, every time you set a set of conditions, time, temperature, and catalyst, making 5 batches to see how conversion would vary from one batch to another. Then you can ask the program to build a statistical model for the standard deviation. And incidentally, you can do the same variable twice. I could have put in conversion percentage twice, told it to build a mathematical model for the standard deviation and to minimize that, to build a model for the mean and try to maximize that. And if I had more than one sample during each run, so I could compute both the mean and standard deviation during each run, then I could have it build different statistical models, one for the standard deviation, one for the mean, and find a single optimal point which does well with respect to both of those measures. Okay. How do we enter repeat measures per run? Well, I didn't really show you that, but I can. I will keep answering questions as long as anybody wants to stick around and listen to it. But basically, this is how you would do it. If you wanted to create an experiment with multiple samples, you'd basically go into the experimental design wizard. You define your responses. I'm just going to take time, like conversion. Okay. You define your experimental factors. Let's just call them factor A, factor B, and factor C. Okay. When you select the design, and let's just go ahead and take the same design that we selected before. The one thing you would do differently is you might tell it, hey, I want 30 samples per run. So every time I do these 20 runs, I'm going to have 30 samples. If you do that, then when Statgraphics creates the design, when I go back to the data book, in tab A, you'll see the design and a column for conversion. You'll also see an additional tab, though, in the data book labeled conversion. And here I would put in the 30 samples for each of the 20 runs. So I'd basically fill out 20 rows by 30 samples. And Statgraphics will automatically compute then actually the mean or standard deviation, whatever you ask for, and put it back into sheet A. So if you had repeat measurements per run, it gives you a second sheet in the data book to put the multiple measurements. Question, last question. I think it's the last one, yeah. Can you use mean even if you have an orthogonal design? Yes. Even if you go in and set up a Taguchi type design in orthogonal array, you can choose to model the mean as well as one of Taguchi's signal-to-noise ratios. Okay, Taguchi prefers certain signal-to-noise ratios, but we still give you the option of building a model for the mean or for the standard deviation or for the coefficient of variation in addition to the Taguchi signal-to-noise ratios. Oops, another question just popped up. How can you create replicates of a design? Okay, where that is, that's under augment design. Oops, I almost canceled the webinar here. Pushed the wrong button. No, once you have done a design, let's say, well, first off, when you're initially creating a design, let me start this whole process again. When you're initially creating a design, you go into the experimental design wizard. You specify the responses. I'll just take all the defaults. Specify the experimental designs. I'll take the defaults. Select the design options. Go through the same process I went before, central composite design. Okay. There is an option initially to replicate the design. it was set to 0 when I did it earlier. If I told it 2, then it actually creates 3 copies, the original and 2 replicates of the original design. Okay, so you end up with multiple rows. And you can see it puts the first copy, it calls it block 1, the second copy block 2, the third copy block 3. Once you've already done a design, though, well, let me close that again. Let's say you've already done a design, and let's open it up, conversion and activity. You've done the design, you've entered the data, you've analyzed your results. If you now want to make a copy, a replicate, you go back to the experimental design window, you go to step 11, augment design, and this will allow you to add a replicate. So I can add a replicate, and it now will add another 20 runs to the bottom of the first. So you either do it when you initially construct the design on one of those dialog boxes, or if it's already done the design, you go to step 11, okay, and there's an option to add replicates at that point. Okay, any other questions pop up? I don't see any other questions, and I've gone well past the hour I promised, but as long as people ask questions, I'm willing to answer them. Okay, we're going to make a copy of this webinar. I hope we've made a recording. We're going to post it on the website so that you can download it and listen to me again if you're not too tired. Okay, well, thanks for attending. I'm going to try maybe in about 2 weeks from now to talk about a few of those other additional topics in design of experiments, things like the RPD designs that I promised. All right, well, thank you. See you in a couple of weeks.